Primary treatment, module 3. This is what we'll talk today, primary treatment systems. Aims and objectives are similar, which I talked about, describing the goals, primary function, key setting point, control points, etc. Headworks we already cleared, pre-biology we already cleared. The target impurity today are TSS, turbidity, and color. However, there could be some industrial environment where you have a higher FOG levels. For example, floating oils, where oil quality, whether it is a free or emulsified, it's important. Fat and temperature, and one must take care of the sediment. That equipment which deals all these oil-related issues called API, American Petrochemical Institute, API separator, because as the name suggests, they have to deal with a lot of petroleum. So there's some design criteria here, which is called maximum horizontal velocity, length to width ratios, depth to width ratios, and this is where the diagram is being shown here, how this looks like. So you have the water coming here inside inlet, it comes right here. Okay, you come here and just take a dip and try to go like this. If you go like this, what is happening? You are releasing all your FOG content somewhere here. And this can be collected and removed via a skim pipe, you can see here. Okay. So this baffle valve number 2, okay, oil retention baffles, which we are talking about, will help that oil will not go here. This is something very simple device, not very complicated, can be designed. Having done that, you have to reach to equalization. Equalization is done to serve the one simple purpose. Okay, yesterday we talked a little about more of providing the linear propagating feed to downstream process at constant flow. Study influent flow patterns, study influent quality variation based on the various operations of flows. Pay special attention to the peaks of pH, oil, temperature, TSS. For example, if your kitchen, the oil, ideally the flow shall be variable based on the level in equalization tank. So this I'll cover in the module 9, process control. Somebody is asking whether it should be always fixed flow. No, but it should be linear propagating. Okay, linear propagating. So that we'll talk about when we are talking about the levels in equalization tank. So the equalization tank is going down, 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 down. So suddenly you have to slow down the pace, because you can't make it empty. And equalization, what is the typical DO level maintained? 0.5. And the other purpose to maintain this DO is just to avoid odor, nothing else. Please, 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 3 times I've said, no biological reactions will be considered in equalization, ever. You give oxygen, that does not mean BOD and COD can be assumed to be reduced because there's no bugs. It happens. Okay, that's a different thing. We don't know why it happens. So that does not mean we start taking it. But biologically, these equipments are not biological equipments. Everything is equalization tank. And it's design feature for readily biodegradable wastewater. You use surface aerators, 0.003 to 0.4 kilowatt energy per meter cube. Or if you're very difficult to waste and all that, then at that times you can use air requirement for diffused aeration, 3.5 to 4 meter cube air per meter cube of the waste. These are typical thumb rule criteria for designing of equalization tank aeration system. Equalization tank is designed on the flow patterns and everything. About construction feature, something important is influent close to the mixing device to prevent short circuiting. The influent pipe which is coming, it should come as close to mixing device as possible. 2, cleaning system for the grease and scum which can accumulate on wall. Because number of times I see the plants, the equalization tank is done, but to clean the debris or anything, even falling leaves from the tree, you should have a system in place. And you should have an overflow here. Sometimes if the flooding is taking place, what should happen? It should not flood everything. So there should be preferably an overflow here, nicely designed, because of whatever reason, and any automation flare and all that, the equalization tank itself is failing, then the water should be not spilling from all the sides. It should spill from only one side called overflow here. And 4th, spray nozzles to break the foams. So just this is the best way you can design equalization tank, because sometimes there could be foam into this. pH control. Now you can see a very complicated slide. The idea is not to complicate, but this is where the pH control is required. The pH controller is not just a pump it is a system where you have an acid tank as well as alkali tank, and whatever is coming to your system, it is going to mix up. You have to take a reading from some point. You have to sense it, and you have to also plot charts. When you are dosing some kind of acid or alkali, how much is the response time for us to really get that indication back on my sensor? It is not that you dose it right now in 3 seconds, whatever pH is coming, you say, oh, that's the right pH. So it takes a little bit of calibration and automation and control in controlling pH. pH is an easy thing to control, but the right device is to have a master controller for the pH. Okay. pH control, why it is important? Because even CO2 is open, right? Is the CO2 is always coming into this particular tank. This is pay special attention to the tank. So whatever theoretical calculation you do for maybe alkali dosing, or acid dosing, they may go haywire because CO2 from an environment comes. CO2 is bicarbonic acid. So I'm not going to explain more into this particular slide. So pH control, CO2 is also important. And what is the control factor for the this section? You have to go for a, again, you understand, operation wise, there only one thing called pumping. Okay, because on peak flow, the pumping demand should go up. If the quality variation is there, the cleaning has to be up and down. Quality means and whatever quality is coming is fine, but if there is any bad material like oil and grease, anything coming to the equalization tank, airflow has no operational significance but a performance significance. Lower the airflow, homogenization will be a problem, as well as odor buildup will take place. So this kind of small slides, take a printout, put it into your operation SOPs of the plant people, and they'll understand what the control factor, even for a tiny equipment like equalization tank. Then we go towards pumping. The design feature of the pump is, it's a part of, again, the headwork pumping, one working, one is standby, rated for 120% of the design flow. Use semi-impeller pumps. Yesterday, some people were asking me questions, so I'll answer, but if you go to the entire modules, then probably all your questions will be answered. Cutter pump, if screens are not effective. Provide suction strainers and footwall, always. Both accessible for dismantling suction line from operation level. So I've seen some slides where what happens is there's this footwall, there's suction wall, but it is not accessible. You have to think of draining the thing. Then, sir, we have a dewatering pump. We pump all the water out of this tank. Then some person will go down. I'm sorry, all this is very bad design. So it should be open from top. You just on the ground floor level only where operator is sitting. You have a flange, you open it, and there should be a proper tie rod so that if by accident, if somebody opens all the flange, the entire shaft and the bottom pipe should not sink into the tank. Then you have to go inside to swim and to search that pipe. So there should be a chain lock along with that. So all these things are very thing. Good thing is to go for Victaulic couplings. Okay, but Victaulic couplings are expensive, so you can go for flange. And this is what is a beautiful primary settler. I'm not getting into detail of what kind of design this it is. It is actually a high rate solid contact reactor kind of design with skimmer arm as well as the overflow. So it's a most complicated of the clarifiers which is probably possible, right? It has got underflow, it has got a scum removal, it has got moving bridge, it has got the suction scrappers. But typically, what is the aim of primary settling is to aim the particulate solids and colloids. How do we do that? So we require a flash mixer. Now I'll come again specifically to this flash mixer. Add chemicals like alum, Fe salts, and mix vigorously at 500 to 700 ppm RPM. What is the advantage of this mixing? This mixing provides the mechanical energy. This mechanical energy does what? It forces the particles to come to each other. So only by providing alum and ferrous sulfate, nothing will happen. You have to shake them up along with that. So the flash mixing. And since this is an electro process, do you require time? The answer is no. Retention time is only 1 to 2 minutes is good enough for flash mixing. Objective is to achieve coagulation, just charge neutralization. No need if chemical injection is not anticipated. Please understand. It is not necessary that every time you require a flash mixing, coagulation, and all that. If you know your particles are already coagulated, you don't require this step. Then we come to flocculation. Add chemicals like cation and polymer, mix slowly at 60 to 100 RPM. Retention time typically is 15 to 30 minutes. Objective is to achieve flocculation, that is binding of coagulated particles to achieve flocculation. Okay, just coagulated particles you're binding. You achieve what? Higher diameter, hence high settling velocity. Denser flocks, therefore higher specific gravity. So both the aim should be clear. The result of a flocculation trial is not only diameter. So if you increase the diameter, but your flock is not dense, but something called a fluffy flock, would you like it? The answer is no, because fluffy flock, the specific gravity will go down. So when you do a flocculation experiment, focus on the increase in the particle size as well as making the flock dense. If you liked all these slides, you select any of the equipment that works. Clariflocculator, HRSCR, Lambda Clarifier, Tube Settler, all are the mechanical versions of the process. Okay, they are not technology in itself. The technology was mixing, coagulation, and flocculation. And then you use any kind of these designs. If you are going for a clariflocculator design, typically flash mixing time is 1 to 2 minutes, flocculation 20 to 30 minutes, rise rate 1.2 to 1.8, retention time is 130 to 180 minutes. And typically in the outlet water quality could be 25 milligram per liter of suspended solids and turbidity of 25 NTU. Beautiful clarifier, I like it. If you go towards high rate solid contact clarifier, you will immediately realize that the rise rate can be as high as 2.4. Why it happens? Because the high rate solid contact clarifier, the distinct benefit which is in the bottom is internal sludge recirculation and hence lower chemical consumption plus higher sludge consistency. So up to 2% of suspended solids on a continuous basis you can get from this kind of clarifiers. Typically, the retention time in the vessel comes down to 95 minutes, 135 minutes. Flocculation time is 15-20 minutes. And one good thing what you see in your screen, I am recommending you to go for a better treated water quality guarantee of TSS 15 and turbidity 15 NTU. So this is a superior clarifier than the clariflocculator. When it comes to plate clarifier, again, it's a beautiful clarifier, very superior. Flash mixing time is only 1 to 2 minutes. Flocculation is 15 minutes. Rise rate is 2 meter cube per hour per meter square on PESA. PESA stands for a term called projected effective surface area. Now on this slide, I have to spend a little time to explain you. Suppose this is one plate. Okay, this is one plate. So what does this plate looks like? This is the plate looks like this. Now if you put into angle, the plate will look like this. And if you project the entire plate, you will have an area here. So what is this area? So this is whatever area you are talking about, L and B, L multiplied by B into cos phi, the angle of inclination. Okay, into cos phi. And if you have n such number of plates, so your area becomes n into L into B into cos phi. But what is the advantage now? These plates are projecting on one another. You can see that these plates are projecting on one another. So there is a lot of overlap area possible, right? And therefore, this kind of equipment, or you can imagine this equipment has actually this much of settling area. But it is packed only in this much area, but it this much of surface area. And therefore, this makes equipment very, very speedy. So you can go at high speed, still maintain the surface area, and therefore retention time comes to 13 to 70 minutes. So what happens to the economics? These kind of designs are the best designs because they are able to save you not only capital money, but also space. But what is the disadvantage of this? I'll just cover in 2 minutes. So you can typically go for good TSS, and the another you can go for good turbidity also. What is one additional distinct benefit? Beautiful benefit is no moving part in the clarifier. Okay, now the second part I'll explain why no moving part in the clarifier. So imagine there is some sludge deposited here, here, here. You can see some tiny dots. Okay, red dots. I'm just putting some red dots. What happens is these dots will start sliding towards bottom of the plate. And when they are sliding, they'll touch each other. And therefore, what is falling from here is a big globule. Okay, something maybe of this size, what I'm talking about. So if the big globules are flocculating, you can have this angle, very steep angle of 45 degrees, and all the sludge will automatically go because of the weight and the force which is acting on the sludge itself. So you don't require a scraper mechanism to keep the sand, guide the sand toward the sludge. This reason, this is the beauty. This reason, this clarifier was very, very popular. It was in India in typically around 1990. Okay, first plant of this nature was given by a company called Ion Exchange India Limited. It is a graver water design, and I have been the fortunate, lucky ones to do my internship on that particular project. CESC, Calcutta Electric Supply Corporation in Kolkata in 1919. The first, plate clarifier installed in India. I was involved in the commissioning team to work on that particular project and understand. Beautiful equipment, lot of good equipments. Therefore, were copied by many companies. And today, 30 years down the line, Everybody knows what is plate clarifier, and many people use it. Okay. This approximately same time, 92, 93, tube settler came in India. It's a good equipment. Distinct benefit is practically no supply of mechanical item, as it is completely in civil. But good thing you can see use when no other option. Why? Because our treated water quality is a problem here. 25 ppm suspended solids is fine, but turbidity control is not possible in this particular design. So what happens is here the feed goes like this, goes to a bundle of tubes, and then you collect the water. And this bundle of tubes are like hexagonal kind of tubes sheets like this, and these kind of sheets. So this area which is there inside, you start calling it tube. Again, same 1 to 2 minutes per hour, flocculation 20 to 30 minutes, 5 to 7 minutes. No attention time. So this I am teaching you, but immediately after teaching, because when you go into the market, you'll find many tube settler in sewage treatment plants and wastewater plants. Never use tube settler in sewage treatment plants. What is the simple reason? The simple reason is here the water is traveling in inclination. Like, can you understand? Because tubes are inclined, 60-degree inclination, and sludge is there in the bottom. So what is this sludge? Is this clay? The answer is no. It is organic matter. So organic matter, whether it is aerobic condition or anaerobic condition, it will do something on its own. Whether you supply air, don't supply, it's organic matter, right? There could be some bugs into it. There could be some changes in its characteristics. And if those changes in characteristics result in releasing some gases, you are in problem, because now the bubble comes here, travels here, strikes here, and then bubble has to travel like this. So in terms of the flow regime, the gases are liberating from here. It is not a good equipment to release the gases. Please understand, right? Number one problem. The another problem is that if you are by chance, whatever little oil and grease is coming. Now again, this area is the rest area. In this area, if the oil and grease decides they want to become droplet, what they will do? They will stop traveling towards top. And if they start traveling to top, they will make all these tubes or plates, whatever it is there, a little bit oleophilic and coated with what we call it is oily substances. And imagine if this plate or tube is coated with some oily substance, the particle which was sticking earlier by hitting this particular place and then sliding down, it hits but never sticks. So it keeps on going still up. So the treated water quality is a big problem in tube settler, in sewage treatment plants, for primary applications or secondary application, both applications. So never use this equipment. Some people ask me, sir, if I don't use tube settler, what I do? I say, use same settler, please remove all the tubes. You let your gases pass, let your oil and grease float on top, not a problem. Okay? Some people do not agree to me, but it's okay. It is not necessary that everybody should agree with me. Alum, typically 50 ppm, 10% concentration. Ferric chloride, 50 ppm, 10% concentration. Lime, 30 ppm, 6% concentration. I will always insist on this word called concentration. Sometimes some people come to me, say, sir, I will prepare a 25% lime solution. I said, okay, please go and prepare first and then come back to me. So you can make a 25 ppm lime slurry, right? You understand the word. You cannot make solution because the solubility of calcium is a question mark, right? How much it will solubilize? Beyond that, it will not solubilize itself. Chemistry doesn't allow you to make more than 6% solution. You can make slush of 25%. You can make sludge of 50% also. 50% water, 50% lime, mix it up. But you don't call it solution then. You call it sludge. So you can make sludge, you can make slush, etc., etc. And therefore, if you want a proper solution of lime, which is a term called milk of lime, not the sludge, milk of lime. Okay, what is milk of lime? Milk of lime means if you take the lime, mix into the water, it will appear milky, and after that you allow it to settle. So when you allow it to settle, what you will find, you can go and do this experiment at home. You will find all the white color material deposited here, but this liquid is transparent, crystal clear. Actually, this liquid which is transparent, crystal clear is calcium hydroxide, CaOH2. I need for pH adjustment this material. I do not need this sludge called calcium carbonate. Getting my point? This sludge is calcium carbonate. This sludge is gypsum, calcium sulfate. I don't need it. For pH adjustment, I need calcium hydroxide. So a good wastewater treatment designer will have something called, somebody will call have lime silo and all that thing. Similarly for alum, for ferric chloride, there is a concentration again. Similarly for polychloride, a lot of time people use polychloride, but polychloride concentration is only 1%. 1% polychloride, then inline dilution to 0.1%. Why? Because if polymer chain is not open, okay, it doesn't function. And if you prepare a 0.1% solution, you are going to have a huge tank. You cannot have that. So make 1% solution, have a mixing tea, like this kind of device. This is a tea. I'll put a tea. 9 part you put water from, pipe. 1 part you pump polymer, okay, of 1% solution. It automatically become 0.1 ppm. If it is a large system, we also give something called a baffle mixing pattern into this particular tea. So polymer, when injected at the point of dosing as a flocculant, should always become 0.1%. And these two are, out of course. This is applicable if your water is being used to this. Typically in wastewater treatment, we do not do alum, ferric chloride, lime, and poly treatment. We just do only poly treatment. But sometimes you may have to do this alum, ferric chloride, and lime treatment in ET if the effluent is mixed with the sewage, and especially in the tertiary area, not the primary or the secondary area. Secondary area, anyway, we don't use any chemical, but in tertiary area, you may have to use chemicals. So after primary settling, you must do a mass balance. Mass balance is done in typically Excel sheets. So tomorrow is the session for the Excel sheets. We'll cover it there. And again, the control factors here are flow fluctuation, inlet TSS fluctuations, additives in FM and NFT, and their effect on operational parameters like sludge removal and launder flow, and performance means treated quality and sludge concentration. So what is happening is, if you look at this kind of slide, we'll see if somebody will say, what are the key control factors for what are the key control factors for clarification? Then you'll say sludge, launder flow, treated sludge, blah blah blah, etc. Okay. Okay. So now we talk about the equipment called CAF, which is not very applicable. This is not very applicable. This is not very applicable for. One second. I had a power issue. Yeah. It is not very applicable for sewage treatment plant, but if I skip this particular slide, I go into the design of this. The cavitation air flotation system is the device which is used if the bulk of the material which you are having is if the bulk of the material which you're having is floating, right? So then the air flotation is assisted. Typically in sewage treatment plant, we don't use air flotation business. Similarly, for a typical wastewater treatment plant, we will not use DAF, dissolved air flotation system. Now, some people do not like me when I say that, but typical sewage treatment plant will not use DAF. But some special sewage treatment plant, we will use DAF. So DAF is in my course. Why? Where it will be used? For example, if somebody says, sir, I do not want microbiology, I still want a sewage treatment plant for gardening purpose. So I'll suggest that gentleman, okay, what you do one thing, you take a DAF and then you go for electrocoagulation and just filter the effluent through ultrafiltration and please put into the garden. The gentleman will ask me, sir, what will happen to the BOD, COD? I'll say, no problems. BOD under 30, COD under 100. No biology required. So it depends where it is an industry. So there's nothing called conventional thing. So DAF is conventionally not used in sewage treatment. But suppose you decide that I want to do a wastewater treatment plant for a restaurant and park and eatery and all those kind of facilities, better to go for DAF, electrocoagulation and filtration rather than a biological system. I do not say that biological system don't work. It won't. It would. But the better to go for a DAF kind of technology. Again, the control factors for the DAF kind of units are how well you remove scum, how well you control the air. These are the two beautiful things. And performance is again treated water quality and sludge concentration, and impact on flow fluctuations, inlet FOG fluctuation, additives in FM and FT, airflow. These are all the important things about the controlling of the DEF units. Then within the primary treatment, whatever sludges are coming, you have to manage the sludge. You can have thickener, centrifuge, and sludge press, dose up to 5 ppm of polyectrolyte, 1% concentration. Inline dilution, you have to again go to 0.1%. Then we talk about, again, pre-treatment method is something called electrocoagulation. So what is the electrocoagulation process? It's a process where there's something called dissolution. Sacrificial anode drive metal ion into water, and water is hydrolyzed at anode. Then coagulation and destabilization takes place because electrons flow freely to the destabilized suspended solids and emulsified oils. So this kind of reactions take place, and then this aggregates start flocculating, and they destabilize the floc. So dissolution, coagulation, and flocculation, all three happen in a single reactor. Who is the driver? Electricity. And who is the driver, which you don't actually see, is electron. Whether the electron transfer takes place when you do typical chemistry called aluminum chloride injection or ferric chloride injection, the answer is yes. That happens because of chemistry. Here it happens because of physics, which is electricity department. So it is absolutely same mechanism, right? But here, since the current is in my hand, current is much more easily controllable than the chemistry. Okay, so that's the difference. So the things can be controlled very nicely here. So you may have some question and answer in this particular session, but I am skipping that question and answer session. I'm trying to tell you two more things, that the tube settler design and the reactivator clarifier design, HRSCR design in Excel files is available. It would be discussed tomorrow, so I'm not showing that Excel sheet today, because tomorrow when I start opening the Excel sheets, everything will be open together. I hope I'm connected and people are listening to me. Good. So allow me to go to the next module. Some of you must have felt that I am very fast today. And the reason for me to be very fast today is you guys are 15 minutes late. So we go to the next module. We'll talk about secondary treatment. Secondary treatment units. Let's put focus on two words. First simple line, degradation, separation. Target is met. That's it. You degrade and you separate, your target is met. And then you don't apply the same formula. So what we can do degradation. We can do degradation by anaerobic process, aerobic process. Biological environment is important. We have to bother about things called fixed films. We have to bother about terms called mixed liquor. When it comes to separation, we'll think of classic separation, decantation, roughing, membrane flotation. Somebody is very loud. Just अगर किसी की आवाज मुझको इन माइक्स के बाद भी सुनाई दे रही तो इसका मतलब गलत है. Roughing, membranes, flotation, etc. So when we talk about this process and then decantation classics, actually a whole lot of technical terms will come into the picture, which are known as BSCOD, that means biological soluble COD, or some people call it biodegradable soluble COD. We will also talk about BPCOD, biodegradable but particulate COD. Then NB particulate COD, which is very interesting. NB particulate COD can be removed, okay? But soluble NB COD cannot be removed, okay? That can be removed only by advanced oxidation techniques. So these kind of terms will come into the picture. And things like anaerobic, activated sludge, MBR, MBBR, SBR. And within the group, we will talk about USB, upflow filters. Along with that, the treatment technology could be Clarifier, tube settler. You might see that in anaerobic, I'm allowing tube settler. Why? Because it's a more a roughing process. After anaerobic, there's always the aerobic process. So sometimes we are doing roughing. I do not bother about the quality issues of the tube settler, right? Because tube settler here is not a terminal unit. But in conventional activated sludge process or any other process, tube settler is the terminal unit. Anaerobic process aims only at C removal. Activated process aims at C, N, and P removal. Now, immediately, somebody might have read in the internet, he may say, no, sir, there is some process called MNOx process. which removes in anaerobic condition the ammonia. Of course, yes, I have also read that process, but there is not a single equipment in India on MMOX process. Okay, so these are all the invented processes, especially done by some people for some purposes, or but that should not be applied unnecessarily to every place. Activated sludge, CNP removal, MBR, CNP removal, MBBR, CNP removal, and SBR against CNP removal. Key distinct feature is SBR is it's a batch aeration and it's a decantation. Nowhere else there is a decantation. In MBBR, you can use DAF. Now you understand the importance of DAF? Why the DAF should be studied? Because DAF is a very good equipment to be used after MBBR. After MBBR, the type of biofilm which is generated or type of microorganisms which are in English word called slough, SLOUGH, they are sloughing off the carrier is so fragile and light that it is better to float it rather than to sediment it. So DAF is a very good equipment to be used after MBBR. And in MBR, we have suspended aeration and membranes, and activated sludge process, we have aeration and clarifier. So one slide. Actually, you are the expert on sewage treatment selection and processes. If you use this combination, what is written here, you don't have problem. The moment you say, oh no, sir, I have MBBBR followed by tube settler. So you yourself know where is the problem. Okay. Only this kind of small presentation and slides, if you keep remembering, because these are not something which are available on the internet or are taken from some article. This is something which the experience of my company and my people and my own past jobs where I used to do, I accumulated out those experience and requested my colleagues to make presentation out of it. Okay. So this is really what I say is the second level of knowledge, which is called intelligence. It is not only knowledge, it is already the intelligence given in this particular slide. This is same. Again, I'll keep on repeating my slides. Let's go back to biodegradation fundamentals after studying this particular slide. We'll keep on doing all these things, but today we are talking about something called COD and BOD removal, nitrogen removal. So let's focus on that in secondary treatment. What we do. So before you treat biologically, again a reminder, and always remind. Balancing flow peaks, mixing tank for pH temperature, the equalization is very, very important. Sedimentation is very, very important. Please remove whatever you can remove in primary clarifier. The rule is simple. Whatever you can remove in primary clarifier, please remove it. Don't send it to my aeration equipment. Enhanced sedimentation, which is called microsand attachment, means there are now roughing technologies available which are beautiful technologies. They are very fast, very speedy, called enhanced sedimentation, where the injection of microsand can help better coagulation and flocculation. Flotation, buoyancy forces, you can use dissolved flotation. Typically, for example, if you are in an environment which is a sewage industry, along with that there is some kind of dairy industry, milk product producing and all those things, DAF could be a better equipment. The screening, barriers like screen sieves, and finally, temperature optimization. Okay, though in sewage it is not important, but again, as we say, we can't devise a separate course for sewage. I can't go here and delete this particular line, cooling and heating, because this is what is required as a fundamental before any biology. Again, we have two choices, aerobic or anaerobic. As I explained during the refresher class, anaerobic gives you methane, so the future technology should be aimed at anaerobic. I'm not going to teach that. Biological treatment process, for what we actually do. So the word is simple, reduce soluble organic carbon. Coagulate non-soluble colloids if not removed before in primary clarifier or DAF. Remove nutrients, nitrogen and phosphorus. And finally, the very important work any plant should do is stabilize organic matter. Because if you do not stabilize sludge, okay, this word sludge, let me write it nicely. This sludge is the main reason for odor in your wastewater treatment plant. Nowhere else. If you cannot manage sludge well or stabilize organic matter well, your wastewater treatment plant will stink. Nobody can save you. Yeah, somebody can come and try to sell you a powder of 1,500 rupees a kilogram that you use in your aeration tank, that you use in equalization tank. It is a special box that will eat everything so that there is no odor or foul smells. Okay, that's a marketing business. But as long as you use organic matter, you keep stabilizing them, sludge you stabilize, you will not have odor in your plant. This slide we covered, but again I repeat, biodegradation is a two-step process where the pollution is converted by eating by bacteria. So bacteria eats the pollution, makes a new cell. And if you provide nutrients, if you provide air, this biomass and water mixture goes and it goes to the separation process. You remove the excess biomass, you get the treated effluent. But this slide is the first time we are seeing this. So it's not an interactive class, but you can do something with me. To reproduce and function properly, organisms need energy, carbon, and nutrients. So how do we get energy? Everybody will give the good answer. That, sir, we eat food and we get energy. Now, food does not give you energy. Energy is given by a simple process called oxidation, which is happening from last 90 minutes with me without me trying it. And that is called breathing process. What you take in is oxygen. What comes out is CO2. So the equation C plus O2 is equal to CO2, which we read in class 9 chemistry, is always happening with any microorganisms, including us. We are a very, very big form of a microorganism. So we breathe, right? So the breathing is the source of energy. That's why in our Indian mythology, a lot of stress is given on how to breathe. Energy is breathing, not eating, which is carbon. Yes, you require carbon because that carbon has to be built up in your body. That carbon has to become glucose, and the glucose will go into your blood, and that will be circulated to and go to right place to burn to give you energy. If you do not have glucose, you are not feeling well. What do? You straight drink glucose. You don't wait for eating samosa to get it converted to glucose. So the carbon is important. And third thing is nutrients, because bugs need nutrients. Our small kids also need nutrients. We require right dose of calcium, right dose of iron, for their growth and things like that. So there are nutrients required for microorganisms also. For what? To reproduce. Because if they keep on reproducing, right, they will have more and more organisms. And more organisms means pollution gone. You can see this beautiful formula, C5H7NO2. Okay. So where is your carbon gone from pollution? Bug body. Where is nitrogen gone? Bug body. Why oxygen is needed? Because if it is not there, cell synthesis will not take place. So these are all very fundamental biosciences. Unfortunately, I'm not a microbiologist, so I cannot tell more about it. But someone who taught me, she talked whole day on only one subject called microbiology in wastewater management. So typically, few slides I can use. So typically, you have carbon source which can come in your body from two C5SNO2 development. How it happens? Either organic COD can give carbon, or inorganic gas also can give carbon. So do you remember anybody who gives carbon and keeps into its cell tissue or a body? The answer is yes, not no. My colleagues are saying no. Tree, what they do? Tree will take carbon from the carbon dioxide and they'll keep it in their body and they'll release the oxygen. So the tree kind of family is known as autotrophic and our kind of family is known as heterotrophic. These are the smallest of the tiniest of the materials possible, heterotrophs and autotrophs. So some people behave like humans, some behave like tree. So if the humans and tree behaves properly, there is no climate change. Remember. So heterotrophic bacteria, autotrophic, if they work properly in tandem with each other, they like each other, then there's absolutely no problem with wastewater management. How do they get energy? Because energy is everything, right? The way I breathe, bugs do not breathe like that, okay? So heterotrophic bacteria do the oxidation of carbonaceous substances called COD. And autotrophic bacteria do oxidation of ammonical substances called ammonium. Yeah, ammonia, okay? And you give some nutrients to them. So some nutrients is given. They can be lacking in the industrial wastewater, so you can add them. But in sewage, you don't have to really add nutrients. So overall, if my goal is COD removal, okay, let me see how I have to develop the bugs, because bugs do this job. So the COD removal will be done by heterotrophic bacteria because they will consume COD for energy and COD for carbon, that means their own body. Autotrophic bacteria will require ammonia for energy and carbon dioxide for the carbon purpose. So 5 slides back, when I was teaching you that bacteria eat pollution, I was wrong. Bacteria don't eat pollution. Now you have two things. Bacteria will breathe pollution and also eat pollution. Okay, this is broken into 2 steps called breathing and eating. Of course, keep giving them nutrient. But there are some beautiful bacteria which do not touch carbon, right? So they breathe ammonia. They take ammonia for energy, but they keep carbon in their body. Carbon from where? Carbon from CO2. And from CO2, where the CO2 will come? The answer is here. This COD for energy means what? C plus O2 is equal to CO2. Okay. So what these people release CO2 is a food of these people. So a combination of heterotrophic bacteria as well as autotrophic bacteria are important in life. You cannot say, no, sir, I want only heterotrophic bacteria in life, right? Then the planet will become the way it is. We want only concrete jungles and we want to live and we'll cut all the trees. You cut all the trees, climate change will happen tomorrow. You don't have to wait for 40 more years. So three major type of microorganisms for all these heterotrophs and autotrophs. I can talk for ages on this particular subject, okay? But let's just restrict to this. Now, these heterotrophs and autotrophs can thrive in aerobic environment, anoxic environment, and anaerobic environment, right? But the answer is anoxic environment. If the bacteria uses nitrate for oxygen, okay, the autotrophs don't perform. The A type don't perform. I'll say A and H, because something may not be very comfortable every time. So here H and A, heterotrophs and autotrophs, both work. Here A cannot, because A's job is to convert ammonia to nitrate. So A cannot do the reversible job of taking oxygen from nitrate. So this job has to be done by a superior friend called heterotroph. So heterotroph will be working in anoxic condition. Anaerobic conditions, since we don't touch ammonia at all, we do not talk about autotrophs. Everything is only heterotrophs. Okay. And among these heterotrophs, now you understand my line, 1-2 line, beautiful line. This time heterotrophs want to work. Till now we have given them nitrate. And now you don't give them nitrate also. So what they will do? Either they will grow or they will die. And if they have to grow, my microbiologists will say, sir, they need oxygen. How can anybody work without oxygen? Your line is wrong. Bacteria operate without any oxygen. Okay. So any oxygen, when I say, is any oxygen supplied by me. They generate their own oxygen. And how anybody will generate the oxygen? Very simple. What is nearby me? Suppose you don't give me food, what I will do? I will eat grass, na? So when you don't give anybody oxygen, what it will do? It will say, okay, H2O, please split. Make hydrogen and oxygen. I need oxygen for my body. Remember, C5H7NO2. That has to be made. So oxygen goes in the body of the bug. So what the hydrogen will do? Hydrogen will say, come on, you cannot leave me naked like this. I am most aggressive material. So hydrogen, at that time, nearby acid is acetic acid. Okay. Nearby acid available is acetic acid. It will strip acetic acid and take all carbon from there and become methane. So the final methanogenesis process will happen because the trigger is the need of oxygen for the cell synthesis. So microbiology plays most important role in anaerobic treatment. And this is what I call the bugs of God. Why I call the bugs of God? I want to spend a minute on this because this is a training program you don't attend often. All the petrochemical products, all the oil and gas, whatever we are extracting from the soil, natural resource exploitation is produced by these beautiful anaerobic bugs much before we came on this particular planet. Okay, they have converted everything to methane, and over a period of time, as you are the organic chemistry experts, some of you have studied organic chemistry, you know the basic material of the organic chemistry. The first material is methane. Remove one H, then it becomes CH3, which can react with something to make a first material called methanol, CH3OH. So methane was the life, and methane would be the life in future. Don't worry about the climate changes. Somebody will continuously keep producing methane. So these microbiological things which I was talking about, they are things like bacteria, protozoas, rotifers, fungi. They live into reactors and they are very happily growing into it. Bacteria is not an animal. Bacteria, in terms of biology is not a Jew material. It's a botany material. It's a plant. So its actual definition is unicellular plant. So you can eat bacteria, you can eat curd. It is still a vegetable because bacteria is a plant. But when bacteria starts growing, some of them become goon and they feel we can eat their own population. Those materials are called protozoas. So once there is a protozoa in the system, protozoa is an indicator there are enough bacteria in the system because protozoas don't eat your COD. They don't breathe your COD. They feed on bacteria. Similarly, rotifers do feed on protozoas. So the presence of rotifers in any system is an indication that there is enough protozoa and there is enough bacteria. So in that curtain raising class when I was talking about, if you do not have a microbiologist in the team, please appoint. This is the reason. So please take a dip slide of aeration tank and go to a microscope and you say, sir, I have got in 5 ml sample 7 numbers of rotifer. I'll smile and say, okay, your plant is beautiful. That's it. We don't have to really test what is MLSS, what is MLVSS, what is SVI. Thousands and thousands of parameters you do not have to really see. Like it's like if your employees look happy, you do not conduct HR surveys, right? If they don't look HR surveys, then you W45 forms to how's your health and everything. So the beauty of a sewage treatment plant is only understanding this slide. That slide where the main job is being done is a biological reactor, which is quite complex ecosystem. If you can understand that well, everything else will perform. Okay. Now, bacteria has got typical habits. They grow. They are prolific eaters. They keep eating. They grow. They grow. They grow. But they also die. So it will not happen that the bacteria will become bacteria to the power n or bacterial power infinity. Some of them will die. So controlling biological community with respect to wastewater characteristics which are coming in, what is going out, new cell production and removal called sludge productions, taking care of the account of the environmental variation like pH, temperature, oxygen, retention time, etc. And a whole lot of trophic chain competition and predation. Competition means I am young, I'll take the food first. I'm young, I'm close to inlet, I will take the food first. That is called competition, right? And predation means, okay, bacteria, while it is doing its job of breathing through COD, eating COD and accumulating in its body called synthesis, also is worried that there can be a nearby predator like protozoa eating me. So all they live very happily in this aeration tank. Aeration tank itself is a big word. And our job as a sewage treatment experts has to control this biological community. Sorry, tough job, but we have to do that. How we can do that? Understanding little bit about their nature. First nature to understand is they are temperature sensitive materials. Most of our wastewater treatment plant happen in mesophilic process zone, neither in cryophilic, which is cold region, not the thermophil, which is the hot region. I don't know more microbiology than this, so you have to study on your own. Temperature affects some physics, which I know very well. First, biological reaction kinetics, higher T, faster reaction. We all are Indians, we know. We all know the reason for China and India's population. It is the temperature. Higher temperature means higher productivity, as simple as that. As simple as that. So all the cold, countries, because all biological reaction kinetics are much better at the elevated temperatures. Gas transfer, higher T means poor oxygen transfer. So your job is to give oxygen through the bubble. So higher temperature means poor oxygen transfer. And settling of the sludge. Remember, rho 1 minus rho 2 A square G divided by 18 mu, where viscosity is the denominator and viscosity is a thing which is temperature dependent. So all those knowledge which you have compared in 8th, 9th, 10th, 11th, 12th class now, you have to please understand on this small word called temperature with respect to your behavior of the plant. So sometimes I get queries from some of the, even wastewater treatment expert. Sir, I do not understand. In the morning only I have this problem. In the night we don't have this problem. So I don't understand morning and night. I don't teach that. I teach temperatures. So you put the log sheet and you say till 27 degrees centigrade, I don't face any problem. But the moment temperature becomes 28, 29, 30, and we have this problem. So that I understand. Then I can explain what could be the reasons. So a good engineer will learn from me And what it will do, it will also educate the same thing in your teams. You all are maybe 30, 40 people listening to me, but these 30, 40 people will have a word of another 15, 20 people, with whom you can share all this. So take my notes. That's the reason Water Today does a very good job, and I'm amongst some serious trainers. I have told even if somebody wants PPT format, let him take PPT format also. But I only worry that PPT format, if people take, they may pitch in their one or two own lines, which is not a good idea. So I prefer to give a PDF format. pH, very, very simple, but very, very important thing, because pH relates to the growth. Remember your pickle. Why your moms make pickle, which are either alkaline pickle or acidic pickle? Is because they know the rate of reaction of the microorganisms is very, very bad at lower pH or higher pH. So you don't make pickle at 7 pH. Your pickles are already 4 pH or 11 plus pH, so that you can preserve it for so many days. Why preservation? No microbial activity. If there is no microbial activity, there may not be any problem. And what is the simple example of microbial activity? Okay, you have the rice, you put some water into it and leave it overnight, and next day see the condition of the rice. Whole night the rice will get fermentation, and this is a sign of the microbial reactions happen on its own before you thinking and starting those kind of reactions. To sum up, our job is to control this environment which is optimum for the growth of the microorganisms involved. And what are the major biological processes? We have three. Aerobic process, where COD and ammonia both can be addressed. Anoxic process, where ammonia can be addressed. Anaerobic process, where COD can be expressed. And two growth models. Suspended growth model, which is classic example is activated sludge. And attached growth model, the classic example is MBBR. And yesterday's question, now somebody is asking me, I don't remember all the names, because I know no names individually, but who asked which question, I don't remember. Did I talk about BOD till now? So please believe me, for becoming a wastewater treatment expert, you don't have to even talk BOD. All calculations, all formulas, all thinking, all estimations are done on COD, because C is the pollution in and the measurement form is OD, oxygen demand of that carbonaceous material. So if you wanted to learn different technologies from me, I'll disappoint you, because these technologies, activated sludge process, moving bed biofilm reactor, membrane bioreactor, sequential batch reactor, biofilters and technique filter, all the five, I can put 2, 3 more, have the same slides which I presented till now. So there's no technological difference. Same heterotrophs, same autotrophs, same behavior pattern, same way they work. So, but they are differentiating technologies. So if I have to be an interactive class, what kind of answer I get? I'm giving you the answer right now. These technologies differ only in the separation techniques. These technologies differ only in the way you grow the bugs. Okay, it is like that. Whether I send my kid to the school every day, he comes back, or I put him into hostel. These are the two different ways I can do the objective education. It doesn't change. The same way, whether I grow bugs on the fixed film or I do the bugs growth in attached suspended, both are their advantages, both are their disadvantage. But in terms of the education process, it remains same. The same way the bugs eating, breathing, reproduction, dying, cremation, all those lifespans remain same in all these 5 technologies. Now, the biggest problem of trickling filter is this, that if clay or inorganic sludges start precipitating along with the biomass, then how do you clean it? You can't clean it. Therefore, trickling filters are out of fashion. But if you can design a trickling filter where you are sure that your Langler saturation index is negative, you never are going to have scaling, and you already have some screens and primary clarifiers where you have removed all the clays, please use biofilters and trickling filters. I use biofilters and trickling filters a lot in potato industry. Understand? You have a DAF. After DAF, we have clarifiers. So there is no clay, there is no sludge, there is no oil coming. It's all beautiful BSCOD, right? BSCOD because of a material called starch. So what we have the first unit, we have trickling filters. What is the one very big advantage of trickling filter is the air consumption is low and their energy consumption per kilogram of COD removed is the lowest. Now, you can say, sir, when I'll become that expert that I can do quickly these kind of calculation which you are doing, you are already the expert. You understand the fundamental first, then design and engineering of each and every process is already done by 2 great scientists called McCuff and Eddy. read their book, everything is given there, including trickling filter design and how the trickling filter is the best design for COD removal. Okay, they have calculated everything per kilogram COD removal, which technology, provided you have what COD? BSCOD, beautiful COD. So all the plants which are from Patanjali, fruit juice, food, potato processing, vegetable processing, okay, you can always go for biofilters kind of technologies. But if you ask me, which one is the best for sewage? Well, all are okay for sewage. For sewage is a cocktail of all kind of waste, right? So all technologies are okay. Depending upon your budgets, you can use any of them. So in my training program, I would teach you in Excel activated sludge design, and I will also teach you the sequential batch design. Moving bed biofilm reactor design, I will not teach you the Excel part. I will, because biology is something which is specific to the know-how generated by you, or I actually don't provide thumb rules, but I will talk about the importance of membrane carriers and things like that. And MBR aeration is the same. So I will little bit touch upon MBR membrane design from engineering perspective rather than any XLS tool. So we go ahead further. We have aeration, biodegradation block diagram where polluted water, wastewater comes, air and nutrients are available. You produce CO2 and some vapor also will go out, H2O, pure water. You get a treated wastewater and you will remove the new biomass. This is now coming to a little bit more chemistry level thing, and please be patient when I try to explain this. So bacteria plus COD plus oxygen plus nutrient, we have two choices. The first choice is, okay, let us enjoy the COD. So that is called breathing process, energy is released. Now when this energy is available to me, then I'll think of reproduction, because energy is required for reproduction. You cannot reproduce if you do not have energy. So this small tiny energy is responsible for bacteria's growth, and then bacteria one fine day said, okay, let us become 1/2. And that is called cell wall division mechanism, by which bacteria becomes 1 to 2 and a new bacteria is formed. That the new bacteria starts breathing independently, also getting energy and growing independently. And then again it divides its cell wall and becomes 2 to 4. 1 cut 2, 2 to 4, 4 to 8. That's the way they grow. So this first two process will be known as oxidation and synthesis. So some carbon will go into cell buildup, which is called Y of carbon. On where the balance will go, 1 minus Y, it will go into oxidation or respiration. सांस लेने में. Okay, the CO2 is gone out of the system. CO2 can remain soluble in the system as per Henry's law. After that, it will start going into the system. And much before that, CO2 goes into the system, out of the system into environment. If there are enough autotroph, they will start feeding on the CO2 liberated by the heterotrophs. So you will autotroph, you will have something similar formula for synthesis. Now, what way I'm trying to show that? This is the first time I'll tell you what is BOD. So the biochemical oxygen demand, the right word is biochemical, not biological. Some people will use the term called BOD, biological oxygen demand. Very shortly, quickly बोल देंगे, biological oxygen demand. No, biological oxygen demand is a beautiful word that is separate. But biochemical oxygen demand is the right word for BOD. So COHNS represent pollution here. Oxygen plus bacteria will make CO2 plus water. Pay attention. I have kept ammonia in the reduced form, NH3. No oxygen given to ammonia. So oxygen given only to which? Bacteria. For which purpose? Oxidation. The second thing is COHNS plus oxygen plus bacteria plus energy is equal to new cell. So new cell formula. Because without energy, you cannot have reproduction. Okay. We require energy. We require heat. So C5H7NO2. Even you can say simple example. Even the chicken have to hatch their eggs to produce a baby. right? They sit on it. What they give? Energy. As simple as that. Reproduction is not possible without energy. Life and growth is not possible because of energy. Energy is everything. And therefore, in our Hindutva, we pay very, very big importance to something called breathing, because breathing gives energy, and energy is everything. So oxidation, synthesis. Till now you understand. Everybody nods in their head. But C5H7NMO2 one day will become old. Though the old is gold, but one day it will become too old to survive. Okay, if it is eaten by protozoa, no problem, a bacteria. But protozoa also will become old one day, na? And this is the basic cell, C5H7NO2. So imagine this is a dead cell. If it is dead cell, right, it will be cremated in the system. So when the cremation in the system takes place, lot of oxygen is consumed, and now this time there is no synthesis. What is happening? Everything is going and becoming CO2. And if everything becomes CO2, right, this is called endogenous respiration. Something like last sans, right? Endogenous respiration. And you can count that there is a requirement of oxygen for so this, okay, for pollution, but there is a requirement of oxygen not for pollution, but for the byproduct of the pollution itself. This is the byproduct of the pollution. So telling that BOD is a pollution is absolutely wrong. The pollution is COD. BOD is a measurement of oxygen required to manage this pollution if you want bugs to manage this. So this is the right understanding of a term called BOD. Typically, this all processes we do for 5 days at 20 degrees centigrade. Then it is called BOD 5. So why ammonia is here? Why ammonia is here? Because right now ammonia is in a reduced state. We do not want autotroph to work. But one fine day, after 5th day, autotroph will say, come on, sir, I have to work. I also need oxygen. So we stop this experiment on the 5th day. We can continue this experiment for 15 days. Believe me, note it down. You can continue this experiment for 15 days, and then whatever oxygen demand you will get, you can write BOD, but just try to add one more word before BOD. You say NBOD. So when you talk about this formula, 5 days, actually you should write CBOD, carbonaceous BOD. Okay, and if you continue this experiment for 15 days, you can remove C and write a word called NBOD, nitrogenous BOD. That means BOD measurement for full nitrification for 15 days. Okay, even you can calculate the air requirement by NBCOD numbers from the laboratories. Now let's understand COD a little bit. COD is the measure of oxygen equivalent of the organic matter, right? Something the way I said COD. But keep understanding this formula, that whenever we are talking about COD, we also have a nearby material called ammonia. Just keep attention to ammonia, because nitrogen has many states. When it is NH3, it is in the reduced state. So I am just writing -3. N2 is the zero state, neither reduced nor oxidized. And there are so many steps of N2 word. 1, 2, 3, 4, 5. Okay. So you leave this nitrogen part. That's why it's written separately in the green. C, H, O, and N. Whatever for C, you require oxygen is this formula. And you calculate the COD. So if you ask me, Sanjeev, can you calculate the CODs of the individual matters? The answer is yes. Actually, when we have certain projects, people do tell us in our waste we have 4 ppm phenol, 17 ppm this material, 15 ppm this material, 12 ppm this material, etc., etc. And we can predict the COD by testing it and also cross-check by applying this simple formula. If it's not a part of the course, but if anybody wants, I can send an XLS. How do you calculate the COD of the individual materials? Let us not go into detail of why COD and BOD are not equal. Actually, I have already told them. A COD and BOD should not be compared in the first place at all. But if somebody wants you to do a comparison, you can read these 5 lines for him. This slide I already covered in a much more depth. Just again trying to tell you the realization what all bugs will do. Bugs will do only for this material. Okay, where is my mouse? Yeah, it's here. Okay, the bugs love this. They only do this. Then this material as well as this one. Okay, out of this only this portion will be taken care by the bugs if you have sufficient HRT, hydraulic retention time. Okay, especially the collide ones. Okay. And you have a proper hydraulic retention time, but it is not only the hydraulic retention time which is important. HRT is important from the perspective of colloidal CODs, but about particulate COD, which is I'm talking about here, suspended, which is slowly biodegradable. Even HRT is not important. The right important term is SRT. Why? Because here what is happening is, okay, let me draw this material. This is one material, a stupid material, which is now particulate, but it has got a beautiful property. Let me take another color pen. It's a beautiful property that it will also stick to the biomass. So what happens is it is not getting washed out of the system because of the lower HRT. HRT is low, water has gone out, hydraulic detention time. But it is sticking to the biomass. It is still a part of the flock. So it is not solubilizing today, but it will solubilize after 20 days. So for example, a banana peel. Cut the banana peel, put into the aeration tank. It will be fragmented in 1000 small particles. But if each of those particles stick to the biomass itself, okay, then do you have any problem? The answer is no. It will hydrolyze after some time. But it will hydrolyze for some time. And for hydrolyzing, if you have to give a lot of time, that time means you are holding the sludge within the system. And therefore, that term is known as solid retention time or sludge retention time, SRT. So SRT, HRT are getting these kind of significance, which you understand only from this slide called COD characterization. Understanding nitrogen is ever more complicated. Please understand this. So what I'm trying to do, if I draw the slide again, we have to oxidize ammonia. Okay, beautiful job. What is to be done? -3 to +5 stage. Is it easy job? The answer is no. And what is denitrification? 5 to 0. So nitrification and denitrification, therefore, are slightly more difficult job. And let me tell you, I am not a biology expert at all, and I will not even touch what happens with the autotrophic bacteria. The way I have given you equation of oxidation, synthesis, endogenous respiration, I will not dare to really talk about them because that's a complex microbiology subject. What I can tell you is there are two beautiful materials. Okay, they do their job. Okay, so okay, it's a small exercise which you can do at home. You need to identify terms related to ammonium nitrogen, inorganic nitrogen, Z-ion nitrogen, nitrate, and nitrogen. Do you do your reading, all this reading yourself? Okay, good. And what is total nitrogen, form of ammonium nitrogen, nitrate, nitrite, organic nitrogen? So many things are there. Okay. But these are the two questions I'm looking for. There's a one family called nitrosobacteria, which does the nitrification part 1. They say, okay, what I can do, I can take NH4 plus, which is in the reduced stage 3, to a stage called NO2 minus. Beyond that, no, I'll become tired, nitrite. So their friend will say, okay, don't worry. Nitrification part 2, we will do that. You make nitrate and we will make it into nitrate. So that here the oxygen is consumed by two different species itself. One convert everything to the level of nitrite, and the second they take it to the level of nitrate. I wish I can teach you more on this, but I do not have actually the capability of that microbiology. But this much is sufficient actually. Now, getting into detail, activated sludge process, therefore, is a process where we will have all the heterotrophs, autotrophs, everything living happily into the system. We will have aeration equipment where they will grow. We will have a separation equipment here, which is a clarifier. the sludge will come out from the bottom, which will be sent to my anoxic tank. It is here. This is the anoxic tower where we will have some kind of denitrification, and from here the feed will go back. Excess sludge will go into the sludge thickener area. From thickener area, it will be pumped towards inside somewhere here where the centrifuges to make the sludges. So typical activated sludge diagram, which is here. What you see here on top are surface aerators. One surface aerator, two surface aerator right now working. This one and this one not working. Probably the surface aerators are linked to the DO of the water. So if the adequate DO is there or not there, the third aerator, and there will be maybe they will work for some time, then after that they'll stop and something like this will work out. It's a huge wastewater treatment plant. What is happening inside this wastewater treatment plant? Let us have a look at this particular slide. So we come, okay, there's so many things in the slide, so please forget everything. So right now the wastewater comes into it, you forget everything, you start giving oxygen. It is a typical activated sludge reactor. So over a period of time, bacteria will start growing. You go to a clarifier, you settle out, you take the bacteria, put it back. So this cycle, you understand? You please keep on repeating this particular process like this. Okay. After some time, you will find, okay, sir, there are enough nitrates now. What is that after some time? 15 days. For complete nitrification to happen, SRT should be minimum 15 days. 15 days time, all your ammonia will start converting to nitrate. Now imagine you have nitrate. So some nitrate will go out here. Okay. So let's imagine the nitrate going out here is 15. And you do not like 15 nitrate. You want it to be less than 15. So what you do, you take the sludge and water which is going from here. You go here, and you put into this particular area. And here you stop oxygen, no oxygen here. So you put a partition wall. So you become an anoxic zone. Now the fresh water is coming in the anoxic zone. So what will happen is whatever RBCOD, which is coming in this particular area, will be first digested or ingested by bacteria called heterotroph. And during that process, heterotrophs will make this 15 ppm of nitrate which is coming into the system to 0 at this point. At this point, nitrate becomes 0. And therefore, this step is known as denitrification. It's written here. So the first step is carbon level 1 removal and denitrification. And then here onwards, no problems. You start C2 and nitrification. So when you are returning the sludge here, can you put a filter here? Only autotroph will, only heterotroph will come, autotroph will not come. Not possible. Both heterotrophs and autotrophs are coming to the system. So somebody was asking me yesterday, sir, how do I design the anoxic tank retention time and sizing, etc. Sir, let me tell you very frankly, even today at my age, it becomes difficult at times for me to design an anoxic system. Because what I have to bother about an anoxic system is one thing I know very well, hydrodegrade I can design, but I really do not know how much time my autotroph will survive with before dying. Because microbiologists also cannot predict their death rate in that much of time because they are complicated equations. I actually do not know, to be very honest. So I go into some ready-made models available from my seniors and my superiors. How do I predict the death rate of autotrophs in the anoxic chain? Because if they are died, so all my efforts of nitrification is wasted. Because till near here I was providing oxygen. Then I have my this time, my bugs are here also without oxygen. Bugs are here without oxygen. They are returning all the way without oxygen. So it is like that. Some of you must have done it as a kid. I'll go into the swimming pool, I'll hold my breath. Now it is up to your capacity how much you can hold up breath. The same situation I have when I am dealing with heterotrophs. I hope Paneer Sarvam is listening. Yesterday I was having a question on anoxic tank, and especially for high temperature. So high temperature, the growth rate is very high in anoxic. Very high. So you are able to do a very good autotrophic growth. But at such a high temperature, even death rate is very high because we are very close, 40. So I'm always worried. Just yesterday I'm giving you the answer, typically 1 to 4 hours. But in high temperature zones, I'll prefer not to go more than 1.5 hours of retention of my biomass here, and not more than this. I'm telling from experience, we can do some formulas and calculations. So this diagram, which looks quite simple, now explained well, so you will be able to understand. And the second part is, which we'll do the designing, designing part tomorrow. That too, again, orientation or designing, because if I start going into each and every cell, it is a 1 day's exercise of doing one Excel. So I'll run through the Excel, and we can do the discussion thereon. Now, 2-3 more slides, because I'm getting a signal from someone that I have to break after 90 minutes. But remember, you all joined 15 minutes late, so I'll take 15 minutes more. Suspended growth of bacteria. Bacteria grow in aggregate called flocks. Flocks are maintained in suspension. So what you're seeing in diagram 1 is not a good flock. Is not a good flock. This also is not a good flock. I want flocks like this. If flocks like this are there, if you put into the tank, they will separate very well. So you have a clear liquid and you have a clear sludge. Biomass estimation is done through two parameters. One is called MLSS and one is called MLVSS. MLSS stands for mixed liquor suspended solid, takes into account all the suspended solids making up to sludge. Living biomass, cell decay, mineral sludges, whatever kachra is there is known as MLSS. But that MLSS, when you heat up or you do ignition, what you will left with will be only inorganics. So what was original minus inorganic becomes what was organic. And what is organic actually? Organic fraction takes account of what? Sludge. What is organic fraction? So organic fraction is a measure of only these things.
I think Mr. Sanjeev is facing some technical issue. Kindly be patient. He will return in a few minutes.
Like that. These are the ratio. For every 5 kilogram of bugs, there should be 1 kilogram of. But neither MLSS nor MLVSS is the true indicator of the bugs, because MLVSS minus cell decay is bugs. So there's no hard and fast rule. The idea you have to understand is lower F by M means low food, more microns. Therefore, the chances of leftover is less. So we will have to just keep those in mind. Then what is sludge production and sludge age? So sludge production we have understood. Remember the biomass which was produced is called sludge. But what is sludge age? So let's understand this particular slide. We have MX means total quantity of sludge in the reactor, which could be okay. I give a number, 1,000.
Mr. Sanjeev, your screen isn't visible. There was a certain pause
Okay.
And you are
I'll,
reconnecting, so your screen is gone quite some time.
okay. Okay. Thank you. For how much time?
No, were you
Just now.
speaking
Okay.
continuously because you were on
Okay.
I think you
Understood.
got disconnected
Understood. I'll just see. I'm not disconnected because I'm talking to you. So there is some other problem.
because
Okay.
there shows that you are still connecting.
I got it. I'll now reshare. Yes. इतना ज्यादा बाहर आके गैलरी में चिल्ला चिल्ली नहीं करने का. Okay, is my screen visible now? Can anybody confirm, please?
Yeah.
Thank you. Is it visible, please?
Yes.
Okay.
So I guess
So
you were in the previous.
I'll go there. I was here.
You were at organic. You're talking about organic
No, it's
oxygen.
okay.
That's when
Did I complete this slide?
you were on this slide.
This one?
No, the one before that. Yeah.
Then you have to tell me you are near me for this purpose only. I spoke for almost 4 minutes without that. Okay. So I come back on this slide. Quantity of bacteria. Biomass estimation is done through MLSS and MLVSS. MLSS means mixed liquor suspended solids, which takes into account the suspended solids making up the sludge, living biomass, cell decay, mineral sludge, etc. Whereas MLVSS takes care only the volatile portion, which takes into account the organic fraction of the sludge. So MLVSS is an indicator of the active biomass, but MLVSS is not biomass. The biomass is actually living biomass plus cell decay. That is the indicator of MLVSS. So active biomass is only the living biomass. So this is the difference when we understand. So even MLVSS is not the true indicator of how much bugs are available. So if you look at my next slide, we have importance of something called food to microorganisms ratio. This is one of the most beautiful slides I can present, the F by M ratio. F means food, which will be consumed by people, and M is microorganisms population. So this is the first time you will see in my screen a parameter uses kgbod. Okay, because now we start calibrating what is digestible in terms of kilogram BOD. And the bug indicator we started taking MLVSS. If you look into some of the Indian books, you will find F by M is equal to BOD divided by MLSS, not MLVSS, but which is okay. See, what happening is it is not important when you are talking about uh, which unit is correct. The significance here is lower the food, better the treated water quality. But lower the food, much more difficult to sustain the biology because some bugs may die. So lower F by M is equal to higher pollution removal. That is the key of takeaway. F by M is not a design number. You know, a lot of time people say F by M is a design number. I'll talk to you further, then you'll understand. F by M is not a design number. Then this next thing is sludge production and sludge age. The sludge production we understand the manufacturing process of C5SNO2, a new biocell, is called sludge production. So you produce sludge. Then what is sludge age? So to understand sludge age, we'll go through this slide. Mx is equal to total quantity of sludge in the reactor, which I may say, okay, it is how much? Okay, 1,000 kilogram. Let's put the simple number, 1,000 kilogram. Kilogram. So sludge is not kilogram, right? Sludge is sludge. So kilogram of biomass. Let us put it. So dry solids. The 1,000 kilogram sludge I have. And PS is the excess sludge removed every day. So suppose every day I decide that I must put 100 kilogram sludge out of the system. Why I'll remove the sludge? Because if I do not increase the sludge, my MLSS and MLVSS will go up. Volume is fixed. If you increase the biomass, then MLSS and MLVSS will go up. So I want to maintain the MLSS and MLVSS, then I'll throw the sludge. So if I start throwing the sludge, what is a simple sludge age? So that means if it is 1,000 kilogram sludge, and if you are throwing 100 kilogram sludge, so that means you are telling the balance 900 kilogram sludge, wait for 9 more days, dost, then I'll send through you. Every day I can throw only 100 kg. People will say, no, we are right now 1,000. I say, no, I can't throw you 1,000. Only 100 I can throw. So the people will keep on waiting. So this waiting is called sludge age. So every time a sludge is there in the system, that any, if you put a mathematical model, any suspended matter in the sludge is in the waiting line for next 10 days, because every day I can throw only 100 kilograms. And then you can put the probability model. Sometimes the fresh sludge goes out, sometimes the old sludge goes out and all that. But in short, what we are talking about, the sludge age is mx by px. And when we calculate mx by px, lot of piping involved, lot of clarifier involved, all these volumes are simply ignored. That is the international way of estimating mx and px. Please understand this. What is sludge age is important. The sludge age is important because higher sludge age means better pollution removal. Higher sludge age means lower sludge production. Why? You hold the sludge, so what will happen? Endogenous respiration. Endogenous respiration means sludge age will go down, because the sludge, which was C5H7NO2, has been converted into CO2. Perfect. So lower sludge production. But will it cost you money? The answer is yes, a fortune, because you have to keep the aeration on for digestion. So that extra oxygen supplied for endogenous respiration, who will provide? You will provide. So it's a more energy consumption. But the good news is, if you do this, you will have possibility of attaining the autotrophs, because you will have lots of CO2 produced during the endogenous respiration. And when that starts happening, then the nitrification starts to take place. Autotrophs start growing when you have lots of CO2 around you. If the food is not there, autotroph will not grow. Even ammonia is there. Even if ammonia is there, if the food is not there, they will not grow. So excess biomass is removed from the plant on a daily basis. Best practice is constant blowout. Now, this is applicable for a very large plant. Okay, in a small plants, don't start saying, "Sir, I am taking your advice and gone for a constant flow," but the flow is so low that my pipe has choked. So don't do that. So in a small plant, the sludge will be removed for maybe 1.5 minutes in full flow once in a day or something like that. Your sludge is coming out. The sludge age is equal to residence time of biomass in the plant. How much time the biomass is into the plant. And any wastewater treatment plant, especially activated sludge reactor, the main operating and control parameters are MLSS, MLVSS concentration, DO concentration, pH, SVI, and SRT. Redox is also important parameters. Redox is like reduction, oxidation, potential. So what is the significance of measuring redox? Well, let's understand the redox from a different table. Biochemical reaction and corresponding ORP value, that is oxidation reduction potential value. So for nitrification, typically the ORP value should be kept between plus 100 to plus 350. Now, sir, whatever this slide, I am trying to show it to you. It is for a very big capacity sewage treatment plant. Don't start putting redox reactor and all those things in a very small treatment plant. So this kind of ranges what is given it. For example, somebody was asking me yesterday, how do I do the biological phosphorus removal in the anaerobic process? So it is not only the process part. You would have to keep the redox value of approximately this in the biological phosphorus removal process. So the redox values are important for what you are trying to do as purposes. So biological, this is not, sometime it will happen two things together, like CBOD degradation with free molecular oxygen. If you go, This is theory. But S2S formation, minus 50 to 250. That means what? What I'm trying to say, if in an aeration tank, you start getting a smell and all that thing, sir, things are turning septic. If it is turning septic, the best way to check is ORP. If you check the ORP and ORP is always positive, things would never become septic. So it is not the DO meter which is important. DO meter is something, but the oxidation reduction potential of that particular place right now is also important. Same as, for example, methane production and all those things. So ORP sensors are the right indicators of what is going to happen, what is right now happening in your process. Okay. You have to supply air. You can supply by diffusers. You can supply by surface aerators. We can also supply from floating surface aerators. So all three are good. If you go for a detailed calculation, you will find some of you might not have visited a large-scale municipal treatment plant, but if you try to visit a large-scale municipal sewage treatment plant, you will never find air blowers. You'll never find the diffusers. You'll find only surface aerator. Why? Because the surface aerators are more energy efficient unit for transfer of oxygen. They are more. So if you're looking at the energy consumption, surface aerators. But it is difficult to really select surface aerators for very small plants. Okay, they are poor in mixing in comparison to the bubble aeration. So the bubble aeration is a normal practice thing in very small plants. But in terms of energy efficiency, it's always the surface aerators which are more energy efficient. And finally, talking about clarifier and sludge production. So if you have some knowledge of water treatment plants, we have a clarifier where typically if 100 parts of water is going in, 98 parts of the water becomes the clear water and 2 parts of the water comes out as the sludge. However, that is absolutely different in a wastewater treatment plant. In a wastewater treatment plant, your water in would be 2, water out from top will be 1, and the return sludge also will be 1. So the lot of water and sludge is going out from the bottom. So it's the detailed engineering design is not the same as the typical clarifier design. Okay, so it's a wastewater treatment clarifiers are slightly different to design. And finally, the key design parameters to remember. Just this is my concluding slide before I break for the session. The F by M ratio means more bacteria, less pollution. Remember. So if you increase the M side, that means F side is reduced, then more bacteria means less pollution. Then quantification of bacteria is indicated in MLSS and MLVSS. That means it tells how much quantum of kilogram of bacteria are available. If MLSS goes down, means MLSVSS will also go down, right? There is a trend, and therefore your quantum of bacteria is going down. If by quantum of bacteria is going down, what it is affecting? It is affecting F by M because M is the quantum of bacteria. Then again you come to sludge age. Sludge age means you are throwing something out, and what you are throwing out is the bacteria. So sludge age alteration alters both F by M as well as MLSS. And fourth thing is aeration requirement. So you will say, Sanjeev, don't confuse. Tell two very simple thing. There's one thing called COD and one thing called biology. That's it. The answer is yes. There is two things. One is COD and one is biology. Balance is all my mathematical models. F by M, MLSS, MLVSS, sludge age, all are interrelated. Actually, out of these three parameters, you can never select all three. If you select MLSS and sludge age, F by M is irrelevant. That automatically will come from these two formulas. If you select F by M and MLSS, then sludge age is automatically fixed. And if you select the first one, F by M and sludge age, then MLSS is automatically fixed. So these three numbers are actually not the design parameters. So design parameter is your experience. Okay, this is my pollution. This is what I want to achieve. So Sanjeev, I think in theory, I should design things for 18 days of sludge age. Okay, excellent. So that is one parameter fixed. Then you will say, based on my experience, let me not keep the MLSS more than 4,000 because I will have settling issue. Because I am going for only settler. So I'll say, no, you are going for SBR kind of settler. No, you can go up to 4,500. Or I'll say, why you worry about settler? You go for MBR. No? There you can go up to 12,000 MLSS. Oh yeah, that is correct. So let us have design parameters 12,000 MLSS and a sludge age of 25 days. What happened to FBM? It already fixed. Food is something which I do not produce in my plant. Food is given by my customer. That is the COD level. So in actual operation parameter also, can I go to a customer and say, sir, you have given me 100 kiloliter KLD plant to design sewage treatment plant, 100 KLD. Please remember my words, what I'm saying. 100 KLD plant. You also said COD is 350. And the same customer says, okay, now my flow rate is only 40 KLD and my COD is also 200. Why the hell your plant is not working? The answer is your plant will not working because you don't have food. As simple as that. So biological wastewater treatment plants are not the mathematical model. So when you are designing a wastewater treatment plant, you will think about, sir, whether you will have 100 KLD flow immediately or you will have 100 kiloliter flow over a period of 2 years. So he'll say, oh, over 2 years. Right now, the some flats are awfully. So initially, there could be only 50 KLD. So you say, okay, sir, then I suggest you have 2 blowers. Half capacity blower will start with. We will run the second blower when it is required. So what you have given, what you have done a bad thing. You have undercut the oxygen supply. That means you have played with the biological kinetics. If you don't give oxygen, will the bugs grow? The answer is no. But you have planned that you do not want your bugs to grow because bugs growing very fast rate means MLSS goes up. MLSS goes up means food is not there. They eat each other, plant collapses. So there are a lot of control parameters. But why I'm spending time on the key design parameter? I'm actually sick of one word from last so many years when I've been teaching. Okay, sir, what you say is okay, but sir, please give me some thumb rule. Na? Well, I can't give some rules because it is the problem of the thumb rule that out of 80 plants in India, you find 72 don't function. 8 will function. It is because of what? Thumb rule. But if you do a proper designing, go and tell people this thing. Everybody is willing to listen if you tell the right thing. You say, sir, even if you want to make curd, after 16 hours, if you keep it in the sun, the curd will become rotten in 18 hours. Right? It's a very simple life science. You cannot make even curd if you do not have that expertise that it is only 4 hours we have to make the curd, and after that it will become very so. So wastewater treatment plant offers these challenges, and I think you have already attended 1.5 days of program. 2.5 days left. I will be at a bigger speed, not talking fundamentals. I'll talk something called hetero, auto, and very, very quick words. But I sure you will be able to understand these words very nicely. Let's try to break for lunch, and then we'll talk about some myths and facts about some processes. Please understand, you get into detail one process, now all the processes are same. Technology is only the difference in separation. So Ramya ji, with your permission, I take a comfort break and I tell everybody that we will meet in 10 minutes. So as you can see, there are 50 plus more slides. So we will try to cover as much as possible by say 6 or maybe 6:05 because today we are running late, and then we'll go to question answers. Myth 1, activated sludge secondary clarifier performs two functions. One, clarification of the overflow and thickening of the underflow. It's absolutely wrong. Only meant for clarification of the overflow because you can't do thickening because you are having at a very high speed the MLSS going out of the system. Then similarly, there are so many myths and facts. For example, secondary as a biological reactor. Can it do COD removal? No, because there's no oxygen here and there's no mixing. Can it do nitrification? No, because you need oxygen and mixing. Can you do denitrification? No, because it will start sludge floating. So you cannot convert into an anoxic tank. You can't do denitrification. P uptake? No, because P uptake needs oxygen. P release? No, because increases effluent P. You cannot design for P release. Filtration? No, you cannot control the flow. And compression and thickening? No predictable uncouples tie to reactor. What I'm trying to say is reactor, it is clarifier's bottom is connected to reactor. How you have to perform in reactor, you have to change the recirculation rates. So you can never talk about compression and thickening here in the clarifier. Why I'm putting these kind of yes and no kind of answers is because this is a huge subject, and I know different people have written different things. I wanted to put my perspective to these things. So truth is, blankets are necessary for secondary clarifiers to work properly, and better performance will result when no blankets are kept in the secondary clarifiers. So people feel that we keep a blanket and all that, and then everything will be better. With two, process control means keeping the MLSS concentration or FM ratio or SRT ratio constant. Now we try what you're trying to achieve. You look at this particular slide. This is a slide which I love. The more I hold the biology, right, what is going to happen is different kind of species are going to see. So free swimming kind of materials. Okay, so relative number of microns versus sludge quality and relative predominance. So this is the good settling rate where you should have sufficient quantity of rotifers, lot of chelates, free swimming chelators, and this is something with microbiology term. But what I'm trying to say is when you have got high FM and low MCRT, you have a phase called stragglers, okay, alone people. And when you have high MCRT and very low FM, okay, which is the typical case of MBR, understand, you have lots of pin flocks, which is a typical case of MBR design. So our activated sludge process and sequential batch reactor process should work into this particular range. For MBBR process, do I bother about all this? The answer is no. We do not bother about all these things, and we do not talk about a term called MLSS. So now we talk about our objective in terms of operational scenario. What is our objective? First, to convert pollution to the sludge, and then second, to manage sludge that settles wells, compacts wells, and flocculates wells. Correct? So the truth too, the process controls mean maintaining a stable optimum sludge quality that is acceptable to the dewatering. That's it. You do not have to really go into this complication and this complication of MLSS and FRT. Just take a simple cylinder and control the stable optimum sludge quality that is acceptable for dewatering purposes. Sludge quality is important. So the control factor in secondary clarifier, which is activated sludge process, there are so many control factors required for secondary treatment. Flow rate, MLSS to MLS-VSS ratio, F by M, SVI, sludge is DO, and inlet load. And you can see the impact of each plus or minus onto COD, BOD, ammonia, TN, SSN, energy. So if I have to plot this into three-dimensional matrix, can I offer 10, 15 thumb rules? The answer is no. We require, when we go to the performance monitoring kind of module, you'll understand what kind of structured modules are required for us to manage these variations plus and minus properly. Now moving forward to the sequential batch reactor. So do we have a change in technology? No. What is changing here is this: anoxic fill, and we got aerated fill, and we go reaction phase where the reaction is taking place. And once the reaction is taking place, we are talking about settle. That's the next phase in which you start to just stopping the air. So you have a clear liquid. Then we have a decantation arm. This decantation arm will help us remove the decant the material. When the decantation takes place, then we can go far towards something called ideal or sludge wasting. These are the simple 6 systems followed in SBR. What is complicated here is now to understand how to cycle time is optimized between 4 to 8 hours depending upon the raw water composition and effluent water quality required. Short cycle means less storage, less volume. And long cycle, if you are doing, you can decide whether you give longer sedimentation time. That means your effluent quality is much better. You are more secure in terms of particulate matters. Or longer aeration time. That means you want to give oxygen, but give slowly. So you have less installed aeration capacity. So typical example is 6 hours where you can have filling, aeration, sedimentation, decantation, and sludge extraction. We would go through an XLS in detail on this particular SBR design tomorrow. Again, the control factor in secondary treatment SBR. Now, I cannot explain all the slides, but something very, very similar to activated sludge process, and something very similar with respect to the variation and then measurement of COD, BOD, ammonia, total nitrogen, SS, and energy. Let's move further. Membrane replace the clarifier. Useful technology. The biomass is separated by a tiny hole, very tiny hole, sometime in the range of maybe 0.1 micrometer to 0.4 micrometer. How do we do that? So now let's look at this particular diagram. I would explain this one is in slightly more details. You have membrane aeration requirement. Why you do the membrane aeration? Because you want this membrane to keep on vibrating a little bit, shaking a little bit. Why you want to shake them up? Because you do not want dirt and MLSS to deposit on them. How much MLSS? Typically to start with 3,000, 4,000, but in a good operated MBR, it could be 12,000 to 13,000. It looks like a slush rather than a suspension. It becomes very, very thick, So when it becomes very, very thick, the chances of it getting, deposited is very, very high. And what you see here, therefore, if you look in a submerged module, in fact, what you see in a picture is Puran. There's no reason I want to promote Puran. It looks more clean. So you have a bottom holder where like a broom, right? You have all the fibers inside. You have air supply. You supply air here. Air will get distributed on its own to various things. So your air is distributed everywhere very nicely. And this portion, okay, you get extraction of the permeate by suction. A lot of designs where you can suck from here, but even from here you suck, absolutely not a problem. The extraction of permeate by suction under the feed water. So what is a typical membrane bioreactor designs? I don't want to read here. Typical membrane bioreactor can be two designs where we have a pre-treated water which is coming to the biological tank. You put all your membranes into the tank and just take it out. The second is you keep the biology separate. You put a recirculation unit. You push the water into it, and whatever is the overflowing, it comes back to it. This is called push design. Okay, where you are pushing the effluent into this membrane tank. Here you take the filtration out, and whatever is the excess water, which will come here. If you have to compare between activated sludge process and MBBR process, okay, I will make a more technical comparison than the marketing ones. You require infrared screen, you require activated sludge reactor, final sedimentation, and the sand filter kind of device. Whereas here you require infrared as well as screens, but you can have some kind of anoxic mixtures. You can see that aeration in a smaller area compared to that, retaining the same biomass. How? Because here the biomass concentration was only 3,000 to 4,000. Here you have a concentration of maybe 10,000. So simple mathematics. To maintain the same sludge as the volume required here is 1/3. Okay, simple mathematics. Here 3,000, here 10,000. Calculation wise, do I have a separate spreadsheet for activated MBR? The answer is no. I have a separate spreadsheet for this design. And this design, membrane area design, you require n number of spreadsheets. Everybody has his own. Sewage has got its own design, hydronautics its own, Torre has got its own design, and most of the time, this membrane manufacturer, they do not give their designs to a consultant. Even me, they don't give design. They say, no, design we will do. I said, okay, don't do the design. So I have one more module to design the plants, but I do not have very specific for one particular membrane. How do we compare conventional vulture activated MBR, which I already covered earlier also in the induction class, so which was a built-up class, is this particular technology will require more space, low sludge concentration, no control on sludge setability, whereas in MBR, you would have robust and flexibility, high treatment efficiency, and low footprint. And which kind of MBR is good? Anything when you operate 12,000 to 15,000, then you really get the benefit. You say, sir, I have the MBR plant, by MLSS is still 3,000. So that means your aeration tank size is still as big as this one. So you work on a higher MLSS. But please understand one thing. There could be some clients which will say, no, for aeration tank design perspective, keep the MLSS not more than 5,000. Because anything goes wrong with the MBR, I can still use my existing clarifier. because at 12,000 MLSs, if anything goes wrong in the MBR, and if you say that MBR repair or replacement will take 4 days, so you cannot say, okay, for the time being, you give your sludge to a activated sludge, clarifier reactor, which you are using earlier. I'll settle it there. No, it will not settle there. I'm telling you right now, it will not settle there, and it will be a big problem. So sometimes, customers are the right people who give the advice how much MLSs they want to maintain. Then we have lots of choices of membrane. Nowadays, even tubular ceramic membranes are being used as MBR membranes. Flat sheet MBRs are very common. Hollow fiber MBRs is common. Tubular organic tubular membranes are also possible. You can also have spiral membranes, but spiral membranes are not typically used on MBR. I have not yet seen people using spiral membranes in MBR. Now, how the MBR operation? Unlike other wastewater treatment plants, MBR operation is a batch process. Let us understand this first. Aeration tank, till whatever wastewater treatment plant we were talking about, I was talking about continuous operation. But what about MBR? Is it a continuous operation? The answer is no, it becomes a batch operation. How? Our wastewater treatment
Mr. Sanjeev?
Okay, I'm sorry, I was disconnected, so I have to reconnect for share again.
You're on the 60-second slide the moment you started
Yeah,
with the
understood.
MBR operation slide.
Okay, I was here. So unlike other wastewater treatment plants, MBR operation is a batch
We are
process.
yet to receive your screen
Yeah,
sharing.
okay. I think it will come. Okay, unlike other wastewater treatment plants, MBR operation is a batch process. But since our wastewater treatment plant is a continuous plant, synergy is very important because you can't stop flow. When
Mr. Sanjeev, your voice is breaking.
my voice is breaking because of the work, I replace that. Okay, do I try one more connection? Okay, give me a second, please, audience.
Yeah, you can rejoin, not an issue.
Okay. So I'm discussing. Okay. Is it more audible now?
Yes. I think you've logged in with two IDs.
No problems. Is it more visible now? Yes, madam. Can you confirm that it is visible? I know I'm not hearing anything from Ramya. Ramya ji?
Yes, we can hear you now.
Okay. And can you see my screen now?
Yes.
Okay. I'm going on full screen, so I think it is visible now.
Yes.
Okay. So unlike other wastewater treatment plants, MBR operation is a batch process. But our wastewater treatment plant is a continuous plant, so synergy is important. Operation is based on the three sequences: filtration, with 10 to 12 minutes you do treatment. Then you have backwashing or relaxation, 30 to 60 seconds. Then you have a degasification phase, which is required by under pressure filtration. You must degasify your some areas in your engineering designs, 10 to 20 seconds. And there could be a de-aeration phase, which is very specific to some membranes. For example, Puran, they allow air to be removed from the fibers itself. So if we talk about membrane fouling, which is what you have to prevent, and one of the methods to do that is membrane aeration, which is to prevent sludge from sticking to the fibers and plates. You can also do something called backwashing, where injection of treated water is in a reverse way in hollow fiber. So typically, this is only possible for hollow fibers. Relaxation, filtration is taught for short time for flat sheets and hollow fibers. Both ways you can do relaxation, and chemical cleaning of the membrane, which is called maintenance cleaning. Typically, we do once in a week. See, now there are some membrane manufacturers, they say we have flat sheet which you can backwash. Fine. So, but this is general rule of design of MBR for fouling control. And these are some interesting slides. Okay, so this is a proprietary name used here called Biosep, which is designed from Veolia. Okay, so what they do there is that we talk about filtration and backwashing pump, maybe duty or standby in single train configuration. You require air separation vessel, item number 2. You require pre-filter and basket filter, that is stainless steel. And you require filtrate reservoir, and finally the manifold valves. And how do you do manual filtration? So you open the VA1 valve, VA3 valve, you start the pump, and you will start getting the permeate. So once you start getting that permeate, the 4-number tank, that is treated water, if you put it into the backward direction, something like this, then it is called the back pulsing or backwash operation. So during backwash operation, what you're injecting in is the permeate, which is already produced by you. So your plant is continuous, okay? Your plant is coming 10 meter cube per hour, but it is, you look at what I'm trying to say. 10 meter cube per hour effluent is coming. You're not stopping it. Suddenly you stop 10 meter cube per hour filtration. That means level in the aeration tank is increasing. Correct or not? Because there is no way effluent is going. And it is increasing, right? Because filtration has been stopped. So that is one phenomenon. The second thing is the level is increasing as well as you are putting additional water, which is going to the MBR tank. Why? Because some treated water is coming back. So again, the levels are changing. So there is an important role of all this kind of hydraulic understanding in MBR designs. Then this is the degasification phase. Why degasification is important, I'll come to that. How you do that, it is again the treated water goes via the pump, but this time the valve VA1 is closed. That means you are not backwashing. Instead, you are opening a valve VA2. That means water will go from this vessel out. When the water goes out from this vessel, what happens to the air? It pushes out air first. Okay, so this is degasification. And why degasification is important? That's the next question. So when you look at the membranes, what membranes are trying to do? They are sucking the permeate. When they are sucking the permeate, can this ensure that they are not sucking any CO2? The answer is no. They will suck. As per Henry law, because there is a vacuum in this particular line, lot of air, oxygen, and carbon dioxide, everything will be sucked into the membrane fiber. It is sucked into the fiber, then it will be. What happened? So when it is sucked in the fiber, then it will be deposited in the entire extraction line somewhere. And if it is in depositing the entire extraction lines over a period of time, it will cause a severe problem of cavitation on these two pumps which are shown into the business. Believe me, gentlemen, I have seen many membrane failures because of cavitation problems in this pump. And the only reason why they have failed is because they do not have degasification system, nothing else. Where ultimately the air bubbles and all those things would have to be pushed toward the suction side, right? So during normal operations, it goes like this. So these bubbles are going to go into the pump suction. And can you send bubbles into the pump suction? The answer is no, it will cause cavitation. You come back to the process after your membrane degasification. This, in short, is the complete filtration cycle in a typical MBR system. If you engineer it well, your performance will be good. And most of this valve need to be automatic because this is what you have to do every hour 4 times because it's a 15-minute cycle. So in a hour 4 times, in a day 100 times. So absolutely no manual control. There has to be automations here. In fact, in some larger plant, we also have level sensor here. Okay, because what will happen is if the air is continuously coming here, water is here, then the air will be filled, right? More and more air filling means what? The air will start building the pressure, right? Because air is getting pressurized. And if this particular equipment's job is to really suck on a continuous basis, because of this more air deposition, what will happen? This air layer will start going low. So we do not want it this level to start going below certain level. Otherwise, there is no purpose of giving this tank. Air is anyway sucked into the line. So the entire purpose of this membrane degasification tank was to make sure that the bubbles go here. So you can put a level switch or a level sensor here as a safety. Now let's talk a little bit on the plate shed MBR, some kind of issues that we have. So this is a typical diagram where we have a flat sheet MBR kind of our product. And if we go into the detail of this, we are going to get into water plus air plus everything. And typically what happens if the air bubble is passing? Can you imagine? The air bubble is passing. What will happen? Air bubble will displace what? Air bubble will displace water. So there would be some place again where the water has to be filled. So this circulation is to be done via air. So this is what this slide is trying to show. If it is not very efficient, what is going to happen? You are going to have some kind of deposit somewhere here, right? Or if this kind of deposits are happening, it is dangerous because only some section is not performing well. So therefore, the balance section is stressed, right? It is working at 15% more capacity than what it is required. So during the filtration phase of 9 minutes, only 90% modules are working. And during cleaning, even those 90% modules are clean, not all. And you don't get to know. And how do you get to know only? You get to know only by instrumentation. So the instrumentation like TMP control, etc., when we go to process controls are very important. So these are some suppliers specific design. I'm just trying to put it to you. Puron typically 250 meters square per meter square of tank. CV 250 meters square per meter square of tank. Torre 70 to 80 meters square per meter square of the tank, and so on and so forth. These are very specific designs which MBR suppliers you have to consult to take. What is important is how do you clean the flat sheet MBRs, because you can't backwash them, right? Some people ask me, you don't backwash them, so if there is a cleaning to be required, how do you do that? So understand, when we say you cannot backwash them, please understand a term There's a difference between something called gravity filtration and pressure filtration. What is the difference between gravity filtration and pressure filtration? In pressure filtration, you don't bother about delta P, you push the water because there's a pump to provide energy. In gravity filtration, you cannot push the water. The flow rate will come down if the delta P is higher, or if the resistance across bed is higher, the delta P, will make sure that the flow is reduced. So flat sheet membranes can be backwashed. This is the diagram. You can do the engineering accordingly. As long as you have this as liquid, okay, layer, and you are pouring the water from a tank which is approximately 1 meter high. So do we have any head? The answer is no, not enough head. So only 1 meter water column head. If you can do like this, you please backwash. No issue with the membranes. You can backwash it with the very low head. So what is done? Usually this is the way the chemical cleaning is done. Okay, typically 6 months if the TMP is exceeding 50 millibar. So if we have to, what we have to measure is TMP. So whatever way we are doing CIP, can I do backwashing the same way, maybe every hour once, or maybe 2 hours after 6 hours? The answer is yes, you can do that as long as you automate the system. Avoid damage of elements. Back pressure should always be under 100 MBAR. Otherwise, these membranes will be permanently damaged. If you have an organic matter deposition, the cleaning chemical is sodium hypochlorite. If you have inorganic matter, the cleaning chemical is citric acid. Again, the control factor for secondary SPRs are same. Fluoride, MLS, MLVSs, TMP, sludges. Now, this is the beautiful technology, membrane and moving wedge biofilm reactor. And what some of you are seeing COD word here. What it represents is sometime this is aeration, this is again aeration, this is anoxic. So this is called pre-anoxic. Sorry, this is pre-anoxic tank which you are here, and pre-anoxic. This is pre-anoxic, and sometimes if you want to do anoxic, that is denitrification in post-treatment. So if you want to do denitrification in post-treatment, my first question will be, you do not have COD, so please add some fresh COD here. If the COD addition is required, typically you can use methanol as a COD addition, a very simple COD, CH3OH, and then you can go for particulate separation. This film everybody knows. In a selective carrier, okay, you grow the biofilms. What is this? Is it plastic? No, the right word is not plastic, because plastic is something, okay, I'm just drawing a diagram, you understand. So if you have water, plastic is something which will always float. It will never go in. So what is the right name of this material? It is called hydroplastic, a plastic which loves water, which is immersed. So that will be first property of this material should be, it should be hydroplastic, it should go into water. The second good property of this water is that its surface should be such that it loves this growth. If the surface does not like this growth at all, for example, plastic, it will never grow on plastic. Like you would have seen some internet videos, keep people, punch a hole into the cap of the mineral water bottle and put it to the aeration tank and start cutting it MBBR. It won't work because nothing will stick on that material. Okay, polycarbonate chips, nothing will stick to that bicarbonate material. So you require a specialized material to develop this hydroplastics. And then there are many design possible. You can have C removal, N removal, separation. You can have roughing with MBBR, then conventional ASP. Okay, then you can have a conventional ASP process and then just do little bit polishing of your effluent. Then you can convert the existing aeration tank into the MBBR tank. All four various choices are possible in a large scale sewage treatment plant for upgradation. But believe me, again, I'll repeat the word again many times. Is the microbiology different? No. Same hydrotroph, same autotroph. Only this time they are attached growth and beautiful attached growth. The growth is attached, but the entire compartment is traveling here and there. The entire carrier can travel like a conventional activated such process. So MBBAR, in terms of the microbiology, understand my word, in terms of the microbiology, is much more superior than MBR. Why? Because it encourages the colony groupism and culture of the bug behavior. You modify the bug behavior. You tell your bug, okay, you sit here, you relax here, okay, and you remain stick to the surface, uh, everything good. So you ask your bugs to behave. That is the first time you started controlling microbiology, which was absolutely wide. They were working the way they were working in all these technologies. So MBBR I always teach last because in the bug behavior wise, it's a much superior technology. They have their own colony, they have their own families. You can say they are some relatives of each other. They all live happily. And sometimes some people move. One protozoa can move from one colony to another colony because protozoa swims. But bacteria, which are going in a sessile mode, where they stick to the surface and grow, they don't move here and there. But rotifer doesn't mind. Rotifer would move here and there. So this is much more organized thing. And that's where the problem is. It's such a disciplined, classroom with so many good students are there. Then whose responsibility is to keep them disciplined? The answer is responsibility is ours. So there is something called biofilm carrier elements. There's something called engineered aeration system. There's something called effluent sieves, that is retain sieves. And all these three areas are not in public domain. They are actually the know-how areas. So most of the time, the large-scale MBBR plants, you will find some people are experts. Their plants work globally and they are doing very good. But there are some big projects in India itself, I don't want to name, who are miserably failed by putting MBBR. Why? Because the third thing was missing, which is called the know-how part. Now, I'll quickly just go through this know-how part in some small slides and presentations. So look, what you are seeing here is an engineered system. So what common sense says, this is a pipe here, which has got stainless steel. There's one more pipe here, which is stainless steel. There's one more pipe here, stainless steel. And this is again one more pipe which is going down. So where are the diffusers? The answer is a good MBBR aeration design does not require diffuser at all. Why you will require diffuser? Now I tell you why here is no diffuser is not required. Is because you understand, even if you put a bubble here, there is so much of plastic here to really hit and get it disintegrated. You do not require micro bubbling at all. You require something called medium bubble. The oxygen transfer rate is enhanced by biofilm carriers. This word is very, very important. Got it? So this aeration design must be very robust, because once you put the water into it, once you put media into it, this entire system, would you like to touch for next 15 years? The answer is no. So what won't work is HDPE, PVC, etc. You have to invest money into this particular project design. This is number one. You require medium bubble, you require even distribution, you want devices that do not clog at all. It has to be maintenance free and it has to keep a very low head loss, right? Because you cannot give water like a Z. I'm just making this sound. You cannot give air like this, because if you are giving air like and that air hits the carrier, what happens to my biofilm? Biofilm will be immediately slowed off. So what will happen is, sir, we have invested money, we have put into MBBR technology, but we never find biofilm the way you show it in my. You will never find, because you have engineer wise, you have done a very bad design. You do not have the know-how. This know-how belongs to certain companies and they are experts into that. And it is always better that if you are looking for that kind of design, better learn from them. Otherwise, just throwing some kind of plastic into a aeration tank does not mean that it will become MBBR. Next is this, you can see here, there's something called MBBR. Various choices are there in terms of screen. So what you're seeing is a very large system. You can see the aeration system here, but what you see here is so many screens, right? What is the purpose of this screen? So if you look at the anoxic tank, there's all this entire wall itself is the screen. Again, the design criteria should be very robust. You should understand the flow pattern. You should understand the flow capacity. These screens should not clog. And finally, these screens should not have any head loss. The aerobic reactor screens are like this. Okay. If I do not know if I can zoom and show, but if a human is standing here, you can understand the size of the screen. And you can also say there are a lot of punch holes into this screen, from where carrier cannot go out, but water will go out. Anoxic and anaerobic reactors. What is the purpose of this screen? If I have to really ask, the purpose of this screen is that water should go out of the reactor without any kind of speed. The speed has to be very slow. Imagine, I'll try to, just try to do a photograph change. I hope it is possible. Yeah. Okay. It's visible. You can see some holes here, right? Okay. It is some holes here in this screen. You can see that, right? What exactly it is doing is, so if I start this plastic carrier, I just copy it and I paste it here, you will understand. So if this carrier is going very near to the screen, do you want a velocity like the answer is no, you do not want velocity. So water in the hole should enter almost at no velocity. Okay. After that, somewhere here from where the main water will exit, right? There could be some velocity. So water, and why there is screen design, you can see there are some holes here, but then there is no hole in a whole lot of screen. Let me draw it. Then for some portion there is no hole, and then again there are a lot of holes. This is where a lot of know-how has gone into development of a screen over a period of time. Which kind of screen is my best design, which allows water to go, but biofilm not to slow. Years of research have gone into the system. It is not just, okay, I have seen in the plant there's a screen, so let me buy a screen and put it. It doesn't work then. So if you ask me, do I have that all that know-how and designs? My answer is yes and no. I know what it is, but I really don't know how it has been arrived. Okay, so I to put it simply, I also know the thumb rules of those kind of things. I know what is the importance of that, but I'm not the real expert to do the engineering calculation, how the number of screens are selected, how the number of holes are decided per screen. But I know it is important, and I have seen some plants, so I can make a more, better guess than you what we are talking about. So typically, I am able to design screens for Indian projects, and I do that. Coming to the advantage of this is MBBR versus a very robust technologies. Again, no recirculation needed. That's one beauty. So in a large scale plant, a lot of energy saving. Like for example, if you are talking about a 5 MLD plant, I'm just putting a number. The 5 MLD plant means you are asking not to operate a 200 meter cube per hour pump on a continuous basis, which is required for sludge recirculation. So that is one energy saving. The second energy saving is in the word which I said, higher oxygen transfer. Higher oxygen transfer means the same amount of bubble gives more DO. It is not important how much air you give. Important is how much air is available to become the DO, which is called oxygen transfer efficiency of a system. So the MBBR system, when designed, can increase the oxygen transfer because bubble strikes the medium. Okay. So there's one more last thing which is important. In fact, there are 2-3 more things I have to tell about it. So you will also find in a detailed design of the system that some nozzles are very close to the wall, to the bottom, and some nozzles are not. So for example, if you look at this section and this section, or if you look at these two different sections, and there are these kind of grids. So 1, 2, 3, 4, 5, 6, 7, 8, 9. If you just put a 1, 2, 3, 4, 5, 6, 7, 8, and there could be some here. So do you think they release the bubble at one place? The answer is no. Why? Because you do want some motions into this reactor. What kind of motions? You want the reactor media to also move like this. Okay? And in some reactor design, the media must move like this. Because if media is not moving and you are feeding water at, suppose, take example of this reactor. And if you start, I'm just putting the pointer here. Okay, let me put the pointer. Take a pen. So I'm just maybe, okay, let's for simplicity take, this is the place where the feed is entering, though it is not entering here. So what happens is, if this media is not moving, all the MBRs, media, which is into this section, will get RBCOD. And rest of the section, you will not get anything. So what happens is, media is continuously recirculated both in this direction as well as in the higher reduction direction, right? And in that process also, you have to continuously avoid slowing. That means the screen plays very, very important role from where they are exiting. So how you enter the water, how you exit is, how the bubble is moving, and how the carrier is moving. These all four combinations are a good know-how for this design. Once designed well, beautiful technology. Absolutely not a problem. But I'll also tell you one more thing. Do you require it for your country? The answer is no. These technologies are typically designed for extreme conditions because you want to protect your biomass. So what are the extreme conditions? Either too cold like Norway, Sweden, etc., or too hot like UAE, etc. So typically Indian climates, do we actually need MBBR? No. A well-designed activated cell process will give as good result as probably an MBBR. So in India, I would prefer a large-scale sewage treatment plants. Either you should go for ASP followed by ultrafiltration, or they just should follow ASP followed by uh, MBR. See, I'm not against MBBR. I'm still saying the MBBR is the best technology, but it is not necessary that whatever is best is required in Indian context. Our waste is typically very nice waste in terms of temperatures, so we can use it. But if there is projects in Jammu and Kashmir where you are sure that the sewage is always 6 months at a very low temperature, then you can think of going for MBBR. Power technique filter. I'll just show the diagram and I'll touch it up. And I'm now the ending presentation right now because it is 6:01 p.m. and we must have some interaction because the idea is not I keep on covering the entire course. Today you guys came 15 minutes late, so I will request everybody to come 15 minutes early tomorrow.